Okay, hi everyone. I'm Amin, and I would like to present a study I did for power electronics simulation using PLECS and Simulink MATLAB. And the study was actually about a paper we presented at PCIM conference. I'm going to put the link to the paper in the description below. And the study was about optimal current sharing in adjustable hybrid switch power converter. So the idea of this kind of configuration is that, so assume that you have a simple two-level three-phase power converter where at each leg, upper and lower part of the leg, A, B, and C, you have a couple of devices operating in parallel, such a valve like this. So we have one MOSFET and two IGBTs in parallel to this one. So that was the configuration we chose for this study. And you can also have more than two IGBTs, like two groups or one more group and something like this. So more complicated configurations. This is also known as hybrid, simple hybrid. But the difference here is that this time we assume that the gate signals can be actually independent of one another. So in other words, you can activate or deactivate IGBT and MOSFET. So, whereas in hybrid, you usually activate both at the same time and deactivate at the same time. So they have the same signal at the gate drive. But with adjustable, it's like gearing mechanism. So you allow this degree of freedom to give you some more efficiency or more reliability and so on. So that was the main purpose of this study. Can we find a, an appropriate uh, gate signals or activation time to activate and deactivate IGBTs and MOSFETs such that we gain efficiency and reliability? That was the main question. The current flows obviously through these devices. So if the current is positive, it's going to flow through either IGBTs or one IGBT or MOSFET, or actually all of them. So you can control which device should be turned on to allow the current flow in. And when the current is negative, is actually it flows through diodes. But the thing is that if you allow the MOSFET to be turned on, you also allow some part of the current to flow from the MOSFET. So then the current flowing through the IGBTs basically is flown through the diodes and not the IGBTs because they're not bidirectional devices. But for MOSFET, is actually the opposite. It's a bidirectional device, so you can allow the current to flow in through the MOSFET in the negative cycle. So anyways, if you want to know more about this work, I refer you to this paper in the description. But now I'm going to show you how I did this simulation because it was an intensive simulation. And what I'm going to show here is not exactly what we did for the paper because we came up with some relatively easier calculation method for gaining efficiency and reliability. But anyways, what I'm going to show here is just a very simple didactic approach for using PLECS for students and for researchers, and what would be the best configuration to run PLECS. And if you have any similar simulation to run, maybe this video will help you for that. So first thing is that I decided to use Simulink instead of doing the whole simulation in PLECS standalone. As you can see here, I'm in Simulink environment and I only have one PLECS block, and everything is obviously inside of this PLECS. Nothing is outside except for this two file block, which records the data into math. We also have this two file block in PLECS. You can also use that one, but I decided to use MATLAB's Simlink's two file block because math is a file type from MATLAB and not from PLECS. So I assume that it is actually more robust to use this one, especially if your simulation is going to run for several days and you don't want to miss any data. And if something crashes in between, you have at least the last data we captured. So I found that this one was more robust for my simulation. So I decided to use the data, to take the data out of this block, PLECS block, and use this two-file uh, Simulink block to record the data in math format. The other thing is that when I compared the PLECS standalone simulation with exactly the same circuit as I have here, I realized that the Simulink, MATLAB Simulink is much faster, like 3 or 4 times faster than PLECS standalone. And so I could trust MATLAB for doing this computation, solving ODEs and everything inside. And the reason I'm using PLECS is because I wanted to have some circuit model quite accurate to simulate the thermal stress, thermal profiles, and especially power losses. Because what I'm looking for is the power loss, switching loss, and conduction loss. These are actually a little bit complicated because they all depend on the operating point, the temperature of the device, and also solving the circuit, KVL, KCL, finding out the IV curves, and also the switching loss. Also, that one depends on many factors. So I trusted Plex for this kind of calculation, calculating the power losses. But then from power loss to the temperature, I did it manually. I had to do it manually. I'm going to come to this later on. But the reason is simply I wanted to know the temperature because for my simulation temperature was a state variable, and I needed to have access to the temperature every time continuously. So I only used Plex to calculate the power losses. Then from power loss to the temperature, we usually have this linear system in between, which is just some several first order systems transfer functions like Foster or Cauer models you use. So, and I also compared it with Plex and realized that they're actually quite close. So that means my calculation for the junction temperature was actually accurate. There was no significant difference between my calculation, what I achieved from Plex in terms of junction temperature calculation. Because as I said, from power loss to the junction temperature is a simple linear system, combination of several linear systems, first order systems. Depending if you're using Foster or Cauer model, you can actually do this, all of these things in linear state space. I'm going to show that in a few minutes. So that's the reason I actually do the calculation in Simulink to speed up and also to have a robust record of data. Okay, let's jump into the simulation. So for this thing, I have here we have 3 devices. Each can be either on or off. So totally, I have to simulate 8 states. But obviously, uh, 0, 0, 0 means that everything is off. I have to discard this state because obviously I want to have the current flow through devices, either one device, 2 or 3. So in general, I will have 7 states to simulate. I'm not going to go into the details of the whole simulation because the purpose of this video is just to show how to do these kind of things in Plex. For example, if I click in this block up here, this is one scenario. So we have the devices here, MOSFET, 2 IGBTs with their diodes, and the current is given from outside because the current uh, is something that you can measure. This is the phase current, for example, for phase A, B, or C. This is the phase current you measure, and you want to pass this current through these devices. And these are the gate drives, gate signals. So they can be either 0 or 1. And we have 3 of them here. And because this current is actually imposed by this variable current source, I had to come up with some circuit because otherwise I get some errors from Plex that the current should flow somewhere. So um, otherwise it's going to be a dead end, so you get errors. So I had to make a very simple H bridge here. So I have this configuration, which is the main configuration, but in order to allow the current to flow through this DC voltage, I actually put this current in an H bridge, kind of H bridge configuration. So I have this IGBT, simple IGBTs here and here. So the current can flow from top, then, for example, through this device, or if it is negative, then it can actually flow from here to here. And if the devices are actually on or off, it can flow from the other direction. So simple as this. But the thing is that this is actually the important part of this simulation. Everything depends on the temperature of the devices. And if you click on these devices, for example, on MOSFET, so you can see here we have some on resistance. In the thermal tab, you can actually specify initial temperature of the device. And this initial temperature is the initial temperature, as it says, the initial temperature of the device right from the beginning of the simulation. But for my simulation that I have actually 7 of these configurations. For example, this configuration at the beginning is 001, meaning that I only activate, I think here I only activate IGBT2. So that means MOSFET is off. This IGBT is also off. The only IGBT which is activated, or the only device which is activated, is this IGBT. So I call this state 001. Okay. And then pretty similar, the next state is 010, means that the other IGBT is actually activated, MOSFET and the last IGBT is off. Or 011 means that both IGBTs are activated. You can see there is a pulse triggered here, and MOSFET is entirely off during the switching period. Everything we talk about here is actually during the switching period. So for this switching period, you only activated these two IGBTs and MOSFET is entirely off. But obviously, there is duty cycle. I think for this simulation of the paper, I chose 50% duty cycle. So for 50% of the time, these two IGBTs are actually activated. And then the rest, everything is actually off. So that means if everything is off, the current is not going to flow from here, this direction down. So we have continuous current from here, this leg, right? So when these devices are deactivated, there is no any path for the current to flow in. So the only way for the current to flow in is through this diode, going from this diode here, and then up again from this diode to the DC link. So because as I said, I had duty cycle of 50%. So for the rest of the switching period, none of these devices is actually activated. So the only way for the current to flow in, if it is positive, is that to flow from this diode through this diode and then back to the DC. So, okay, I'm saying this because I'm simulating in parallel, basically, many states, like many, yeah, states like 001, 010, 011. And for example, 100 means that only MOSFET is activated, but obviously, as I said, only 50% of the switching period. You can play also with the duty cycle, but I just kept it constant as at 50%. And the last state is 111, means that all of the devices is like hybrid situation. All of these devices, two IGBTs and also the MOSFET, are activating and deactivating at the same time. So, and I'm going to choose from these 7 states which one gives me the best efficiency, for example. By efficiency, I mean the minimum power loss, and or which one gives me the best reliability or thermal stress for the whole circuit. So these are actually KPIs, for example. So for doing this simulation, I have to run these circuits in parallel. And I have to run these 7 circuits all in parallel and get the results. And the results are actually junction temperature. Let me click on here. So what I'm measuring here is that I measure conduction losses for each device. I had one MOSFET, two IGBTs with their antiparallel diodes. So I measured conduction loss plus the switching losses for MOSFET, for IGBT, diodes, perhaps negligible. And then I sum them up to get for each device the total power loss, which is a combination of these two, summation of power switching and conduction loss. And then I fit this into my own circuit. As I said, I'm calculating the temperature myself, temperature junction temperatures here. As you see, I uh, built some state space, simple state space, x that equals ax plus bu, and so on. So there's this integrator here. So this simulation, this block simulates the junction temperature for each device, for MOSFET, for IGBTs, for diodes, and the other IGBT and diode pair. And the reason why I'm doing this is because, as I said earlier, so for each device, you only can set the initial temperature of the device right at the beginning of the simulation. But the thing is that what I what I'm doing here is that I'm running 7 simulations in parallel, or they're running here, and then I'm going to pick the best one in terms of efficiency or reliability or any other KPIs. So they obviously they all provide different temperature, different junction temperature, different power losses because they have different activation, right? So the one that gives me the best for each switching period, I'm going to use that one for the next switching period. So that means I need to keep track of the junction temperature for the best one for every switching period. So for example, I assume that you are at switching period number K and you run this simulation and realize, okay, this junction temperatures or this power losses for this configuration 001 gives you the best KPI. So now you need to record the junction temperatures here and then feed them back to all of these circuits because they all have to start with the temperature of the previous best solution. So that's why I had to kind of do the temperature calculation myself because I needed to keep track of the temperature. And as you can see, I had to come up with some strange mechanism here because, as I said, I need to impose a temperature from outside, and which depends on the temperature I calculated here, right, in this block. So, and the way I did this is actually very interesting. So I changed the thermal behavior of these devices to something very close to 0. If I can find it here, yep, let me, if thermal, you see, the values for example, for Cower of this MOSFET is almost 0, very close to 0. And that means any temperature can quickly uh, impact the junction. And then also I have resistor here, thermal resistor, which is also a very small number, 10 to minus 5. And here I have variable uh, temperature, controlled temperature, which is grounded. So anything I apply here to this signal can quickly affect the junction temperature almost immediately. So that means with this mechanism, with 0 here, and also with the RC network, which is close to 0 here, I can basically, and also this heatsink I forgot to mention, this also has a very low number in thermal capacitance. So anything you do here can immediately affect the junction temperature. In other words, I actually set the junction temperature of this device through this signal. Very simple. And the reason again for doing this is because initial temperature right at the beginning of each switching period is actually given from outside, from the optimization and so on. Because optimization is going to pick the best state for each switching period, And then according to that, you have to keep track of the junction temperature of the corresponding best uh, state. So that means if you, for example, if the optimal state for one switching period is this guy, so you need to feed back the temperature to all other circuits for the next switching period. Okay. So through this mechanism, similar for IGBTs and also diodes, I can set basically the junction temperatures from outside. Okay. So for this block, if I zoom in, I give the pulse. That's the main pulse of the phase current with the duty cycle given inside. And then I have the states of the IGBTs and also the temperatures. These states are actually, again, calculated here because we have RC network of Foster and Cauer model. They're, as I said, they're a combination of several linear systems. So they can have like 4 or 5 or even 6 number of states for each one. So you need to actually keep track of the states here. So these are the states coming from the temperature calculation according to the Foster or Cauer model. These are the temperatures of the best solution from the previous switching period. And this is the current fitting here. And then you at the output, you get the current for each device, IGBTs, MOSFETs, and also the junction temperature. So this calculation is identical for all of these states or configuration, and they're all fed into this to this block. These blocks actually calculate the cost function. So for my case, for example, I wanted to calculate the summation of junction temperatures to the power of 2 or the variance of the junction temperatures. So then here we have a square operator and then some gains, some weights, sum them up here. And then obviously some states are discarded because of their limit. There's a limit on the current for each device. So if we, for example, if the current is large, you cannot just have this configuration, only one IGBT on because the current is too high, so it can damage the IGBT. For that case, this state is actually discarded because the current is beyond the limit of the IGBT. So this is checked actually through this mechanism here. Very simple mechanism. And then outside, as the output, you get the cost value for each configuration. And they all go into this C script. Because I realized that if you do the C script block, the simulation can actually run much, much faster. If instead of doing all of these things in blocks, if you can do the coding in C is much, much faster. So this C script is a very simple script. It has to find out which one is the minimum cost function, gives you the minimum cost value, and then uh, calculate the corresponding signal or gate drives, those numbers 001 or 111 and so on. So inside you simply specify the number of outputs, inputs, and the code is similar as this to calculate just the minimum number of which one is the minimum, and also calculate the corresponding gate signals, those binary numbers. Those binary numbers are actually multiplied by the pulse, the main pulse I had, and then this is the main simulation for that particular switching period. So again, you have the circuit again here. You have this circuit. Again, the junction temperatures are given from outside. And then here, the signals are now given from the optimization, which configuration actually gave the minimum cost function. So you apply the binary values here. The current is exactly the same as before. So, and then you again calculate the uh, power losses and then also the temperatures again. And here you also achieve the state values. So this thing is actually the main engine for calculating the through junction temperatures, because this is the main simulation. It's like this is my real circuit. before up to here is everything is actually simulation, purely simulation, or we can do it in scripts. So these are my scripts, and here I calculate which one gives me the minimum cost function, and then I apply it to the real system. So this is actually kind of a real system, simulating the real scenario to calculate it. And these are actually the junction temperatures, which are then fed into the outside to the output, which is then recorded by the two-file block in MATLAB. There are a couple of things here I wanted to address. One is that, okay, as we said, there is this junction temperatures which is set from outside, and for doing this, you need to change the thermal and capacitance resistance to very low number values. The other thing is that this is about switching losses. Switching losses, actually, you need to do some kind of periodic impulse average, like this block, which uh, kind of calculates the average switching loss over the switching period, because the output of this block is the energy, and you need to convert it to power. So, but the problem is that this block, there is a lag of a switching period. So you only get the output after one switching period. So there is kind of a one step delay. Whereas this block, which calculates the conduction loss, is actually instantaneous. So you get the conduction loss instantaneously, whereas this block only gives you the switching loss from the previous switching period. So this is kind of uh, approximation of the current or instantaneous switching loss, but we know this is not exactly the current switching loss. This is the switching loss from the previous configuration, previous switching period. This is actually one thing. The other thing is just this calculation. As I mentioned, they're calculating the junction temperatures according to some state space manually. So these are matrices given from MATLAB script. And here we have the current calculation, just to make sure the currents are below the limit. And also, in order to speed up the simulation, I had to run uh, this sine wave also in a C script code, very simple C code here to generate sine wave. But the problem is with the timing, because this simulation for each model, you get the power losses here instantaneously, and then you also calculate the temperatures and everything here, and then they're all fed into this cost function and C script. So in order to speed up the simulation, we need to run this C code not continuously, rather for discrete samples of 2 times the switching period. So this is a very careful selection because we need to synchronize everything. So these states or temperatures given into these blocks should be actually valid temperatures coming from the real simulator, which is given here. So in order to make sure that everything is synchronized, you need to adjust these blocks carefully. And also here in the main signal, or this is actually your main current. You see, I'm getting the current signal from here, simple sine wave. But the thing is that theoretically it should be simple sine wave, but because here we have this complicated blocks calculating the model and then they're fed into the real system, there's kind of lag here. So I had to do some mechanism here, complicated mechanism here to generate that uh, correct current profile for each switching period. Yeah, that's it from my side. I wanted to address this using this kind of complicated simulation. And the problem here is that, first of all, I had to do all of these things because I couldn't adjust the temperature of the devices during the simulation. The only way is that you can give one single initial temperature, which is valid only for the uh, beginning of the simulation. But then I had to adjust this temperature through this mechanism given here. I hope this simulation helps for those who are interested to do some modulation techniques, studying the thermal stress or power losses. I hope they can actually grab some stuff from this work and also use it in coming up with the best KPI. It's still, for me, it's not clear which one is the best KPI. So here I used simple variance of the temperature profiles and also used maximum, worst case temperature, stress, and so on. But it's still, we can play around and try to come up with another cost function that corresponds to the real thermal stress. Okay, thanks.